Welcome back, AP Stats. This is quiz 9 of the Barron's the packet that I gave you guys for quiz 8 and 9. So let's just get straight on to the questions and get started. Number 1, which of the following is a correct conclusion? So we have the slope and the y-intercept, all these wonderful things. Remember, we are just completely going to disregard that. SAT in the variable column indicates that the SAT score is a dependent response. We always talked about how this is explanatory. Yes. Correlation is 0.875. Now, the reason why I am not going to say that this is the answer is because, first of all, you have to square root the 0.761. And I do believe you guys do get that. Don't jump into conclusions and say that is going to be the correct conclusion, because look at your the slope. The slope is negative. So which means your overall scatter plot has to show a generally like a negative trend. So your correlation cannot be a positive number. Rather, it's going to be negative 0.875. If you square root something, remember there's a plus and minus that comes along with it. So please keep in mind for those. So that's why B is not going to be the correct answer. The y-intercept indicates the mean combined SAT scores had a percent of taking the exam. Okay, so this one, y-intercept indicates that the mean combined SAT score, if percent of students taking the exam, has no effect on combined SAT scores. I really don't know what this is talking about, so I'm just going to leave it on the side. The R-squared value indicates that the residual plot does not show a strong pattern. R-squared value has nothing to do with that. It just shows the variations. It does not show a strong pattern. We can never expect that to happen unless we actually get the residual plot itself. The last one, schools with lower percentages of students taking the exam tend to have higher average combined SAT scores. So that means lower percentage of students taking the exam tend to have a higher. So the Y variable, let's take a look here. The X variable is your SAT, and percentage of students who took the exam at 100 in these schools. Data on average combined SAT scores and percentage of students who took the exam at 100. So I'm assuming that this is SAT scores and this is the percent of students who took it. So the schools with lower percentages tend to have higher average SAT scores. Okay, that makes sense, because if we're talking about here, this is low percentages, but then your SAT scores is high, versus when you have a higher percentage of students who are taking it, you have a low average SAT scores. So this is a general trend of the idea of what you're looking at. See, the y-intercept just straight up indicates the fact that if you had a 0%, if you had a the X variable SAT to be 0, then the percentage of students who actually gets this, I think I might have made it like, I'm not sure if I have to change those two variables, but the y-intercept just indicates the initial value of the score. I think it should be the other way around. Percentage of students and the SAT scores. SAT in the variable indicates the SAT score is the dependent variable. No, actually, no, that's not true. So I'm just going to leave it like this. This has to be the correct way. But what this is talking about is that the y-intercept of 1176, that should just be your straight up score when you have 0 for your X. That's what the y-intercept is talking about. It's not talking about the mean combined score. If percentage of students taking the exam has no effect, percentage of students took it is like actually like 0%. But I just do not understand why these should not be changed. But anyways, it clearly describes the relationship between the two, so I think it should be fine. Number 2, suppose the correlation is negative, given 2 points on the scatter plot, which of the two following is possible? All right, remember, this is a scatter plot. You can't expect it to be just those 2 points. Rather, you have to expect that there is going to be a bunch of points like that all throughout the system. So here, when we say the first point has a larger X value, and the smaller Y value than the second point. Okay, well, first of all, that's clearly true if I just pick those 2 points. If it's a larger, it has a smaller Y value. So 1 is definitely true. So I'm going to eliminate the one that does not have 1. The first point has a larger X value and a larger Y value than a second point. So let's say that, for example, something like this, the first point has a large X value and large Y value compared to the second point. Okay, so I think two is true, but 1, let me just go over this with you real quick. Sorry, because I kind of drew it wrong here. So that's the linear line. So the first point, I'm assuming that that's the left point, and this is the second point is your right point. So if your left point has a larger x value, so let's say something like this right here, smaller y, it's larger value and a smaller y value, then the second point. So the second point could be like on the right hand side. If a dot is somewhere over, let's say, larger x value, the first point has a larger x value than this and the smaller y value. Well, the smaller y value is definitely for certain. The second, okay, so first and second point, I don't think it has to be left and right, but you can just pick any 2 points from the scatter plot, right? So it can have a smaller x value and the large value, but these 2 points could still be part of your part of the scatter plot points. So 1 and 2 is definitely true. So if it doesn't contain 2, I'm also going to eliminate those. So it seems to me the only answer choice I have is E. The first point has a smaller x value and a larger y value than the second point. Yes, you can okay, so that's smaller x value than this, larger y value than that, and that has a negative correlation. So everything makes sense. This one is the easiest one. So when you see that equation next time, just remember to just plug it in. The only thing you have to do is just plug 2 into x, 5 into y. 5 is 6 plus b. B is -1, so it's E. The slope still remains the same. It still should be 3 for your linear regression equation. Number 4, which of the following statement about the correlation R is true? 0.2 means 20%, and that does not mean anything. It just means 0.2 measures the strength in which how good of a measurement the line is to the dots. Perfect correlation, that is when the points lie exactly on a straight line, lies in R is equal to 0. Perfect correlation should be R is equal to 1 or R is equal to -1. 0 means no correlation. Correlation is not affected by which variable is called X and which is called Y. This is actually absolutely true. Correlation does not get impacted by anything unless you're multiplying by -1. We've actually established that in the previous video. Correlation is not impacted by extreme values. It definitely gets impacted by extreme values. Imagine, I have this where it gives you only correlation of 0, but an extreme value up here can actually increase your correlation by a dramatic amount. Correlation of 0.75 indicates that it's 3 times as linear. We are not measuring correlation in terms of quantitative measurement. Rather, it's just an indicator as to how good a fit is. As one with the correlation, it doesn't mean it's 3 times better. It's just better, but it's not 3 times better. The correct answer here should be C. Which of the following statement is about residuals if the least squares regression line are true? For tomorrow, please note that the mean of the residuals is always 0. The sum of all the residuals. The sum of all the residuals is always 0. That's something that you must remember. The regression line for a residual plot is a horizontal line, it says. Let's see. So for basically the regression line, let me just exit out of this one. Okay, so the regression line for a residual plot is a horizontal line. It could be a horizontal line, but then, the regression line for a residual plot, the residual plot should always be a horizontal line. Yes, that's absolutely true because that's when your residual is actually at 0. The definite pattern in the residual plot is an indication that a nonlinear model show a better fit to the data than the straight regression line. The definite pattern in the residual plot is an indication of the nonlinear model. Yes, because as long as we see a pattern in there, we never ever want to use we don't want to be using a linear plot to indicate anything. So it's actually 1, 2, or 3, and I think that should be the correct answer. In a study of winning percentage in home game versus an average home attendance for the professional baseball games, the resulting regression line is, okay, so we have this. What is the residual if a team has a winning percentage of 55% with an average attendance of 34,000? So again, we just want to plug in the 34,000 into this equation right here. Oh, I lost my calculator, so I have to start over. All right, so let me just go all the way to this. All right, so the equation says 0.0003 times 34,000 for the attendance plus 44. So I believe it's like 54.2% for the predicted, but your actual is 55. So you do that. And so it's about 0.8% of a difference has a winning percentage. So the residual should be positive, so it should be C for 6, which is correct answer. All right, 7. Suppose the correlation between two variables is negative 0.57. If each of the y-scores is multiplied by -1, it does not change anything in terms of your correlation coefficient. So you're going to eliminate B or D. So if it gets multiplied by, oh, wait a minute. I'm sorry, that's not true, because if your y values gets multiplied by -1, which means whatever was positive now goes like this. So whatever was negative now it becomes positive, it just gets reflected. So you are actually definitely it's going to impact the change into your correlation coefficient of being a positive, and it slopes up to the right. It slopes down to, no, it slopes up to the right, and correlation is a positive number. So it should be 7 is B. A study of selling prices of homes in a Southern California community versus size of homes shows a moderate positive linear association. The least squares regression equation is 35. Okay, blah, blah, blah. What does a linear mean in this context? The points in the line, scatter plot line up in a straight line. They don't straight up line up in a straight line. That's it. They have a general trend of being a straight line, but it doesn't mean that it's going to straight up like line up in that manner. There's no distinct pattern in the residual plot. That's good. Okay, so this means a linear in terms of residual plot. The coefficient of determination R is large. Okay, close to being 1. That's true, because if R is being close to 1, it means that it's very, very linear in this context. So these two are actually good answers. As home size increased by 1,000, the selling price tends to change by a constant amount on average. That's just describing what the slope is, by the way. Each increase of 1,000 square feet, the house, okay, that's also another slope. So this really describes D&E is just all about the slope right here. What does the linear line mean? Okay, so maybe, wait a minute. So I have to reread this one. As home size increases by 1,000 square feet, the selling price tends to change by a constant amount. I love the word tens here. First of all, E is out because it's straight up describing about the slope here. For number 8, they said it was D, but for quite honestly, for this one, let me just go over why all the other ones makes no sense. There's no distinct pattern in the residual plot. So that definitely shows that it's going to be, it's a moderate positive linear association in the scatter plot here. Okay, so this one is talking about the residual plot. Yes, linear trend in the scatter plot will translate into a randomness in the residual plot. But because we are strictly talking about the linearity in the scatter plot here, we want to eliminate B because it's talking about the residual plot. That's the main reason. The coefficient of determination R squared is large, close to being 1. That determines the positive relationship, which definitely has in this case. The linear means that as one increases, the other one will increase in a linear fashion. Okay, yes. As one increases, the other, when I say the one and the other, it means the variables. The other will increase or decrease in the same particular manner, like same particular amount. So sorry for this one, but this is just straight up my fault. The reason why, all of B and C makes absolute sense, but the only problem is that there was another similar question like this in the previous quiz. They always start up with the answer as home increases, as X variable increases. That's what they want you to describe in terms of the linearity. Yes, there's other ways to go on about it. There's other ways to describe what linear means. This just proves that the linear model is the best fit. Randomness in the residual plot. This means that the coefficient determination of R is very close to 1. That means that the dots are very close to the line. Quite honestly, that's what it means. Dots close to the line. Okay. But it doesn't mean that the R could be negative for R like here. If R is -1, then R squared is also, when you square it, it becomes +1. So how do you know if R is negative or positive? You never know that. The coefficient of determination is large, regular. Like that just means dots are closer. It doesn't have anything to do with linearity though. The linearity comes from the fact that when one increases, there's a slope. There's a certain slope that happens in this equation. So this one is D, particularly because E is just straight up talking about the number of the slope, not the actual definition of what linearity means. As one increases, the other increases. As home increases, the selling price tends to change by a constant amount. Hence, it's a linear relationship because there's a rise over run in a constant manner like that. It's not going to be exponential where, as one x increases, the y increases by non-constant amount because it keeps on getting more and more and more. Because it says tends to change by constant, it shows that this is going to be a linear fashion. Okay. Again, it's just a play on words, guys. Honestly, that's basically what it comes down to. Does a lower sun exposure as measured by a greater distance from the equator result in lower incidence of skin cancer? Okay, so 100 northern hemisphere locales show a strong negative linear association. Okay, again, what does the strong represent? So now we're talking about the strong. The strong, I believe, they should come from the fact that, well, let's just read over this and just make sure what happens. More sun exposure causes greater number of skin cancer deaths. This is just cause and effect, so I really don't like A. So for 9, I'm just going to have that. Okay, so more sun exposure is associated with greater number of skin cancer. More sun associated with greater number of skin cancer deaths. Okay, but then it's a negative association. So as one increases, the other one should decrease. As measured by greater, this is resulting in lower. Yeah, so this is actually not a strong in this context. I mean, this is definitely strong, but it's not related to this context at all. A locale's incidence of skin cancer deaths has a linear association with its latitude. Okay, it could have a linear association, but it's not talking about the strength. A least squares model predicts that the greater the latitude, the lower the average incidence of skin cancer. So we are using a least squares regression model to predict that the greater the latitude, the lower the average incidence of skin cancer. Okay, I like D, but let's read E here. The actual incidence of skin cancer at a given latitude will be very close to what is predicted by the least squares regression model. Okay, all right, so let's talk about the strength here. D predicts what's going to happen, and this actually means negative. What does negative mean in terms of the context? Because if you read this carefully, least squares regression model predicts that the greater the latitude, as one increases, the other decreases. So that is talking about the negative relationship between the two. When we're talking about the strength, because we're talking about what does the strong mean in the context, you got to be careful. The strong means that the dots are very close to the line. Like the R value is very high. When R values are high, it means that the dot is very close to the line. So the actual instance of skin cancer at a given latitude will be very close to what is predicted by the least squares regression model. So that should be E for this one. C, a local incidence of skin cancer deaths has a linear association. Again, this is just talking about the linearity. So I mean, they could just go pick any of these things. What does strong mean? What does negative mean? What does linearity, like linear mean? Like this is more closely related to like a linearity of the two in the context. This is talking about the negative, and this is definitely talking about the strength. If I actually had to give a reason as to why C or D does not work. All right, so that was a handful. Number 10. Now we're down to something that's quite easy. SY 5/3 times R is your slope. Unfortunately, I don't know what R is. Okay, well, just let's take a look at what we're given. 2, 4 is a pair of point that you can use to plug it into your every single one of your choices and quite eliminate them. So for example, if I plug in 2 for X here, do I get a 4 for Y? No. 4 for this one, 4 for this one, not for this one, and I get this one. So it's either B, it's among the B, C, and E. But the biggest problem as to why the answer is going to be E for this one is because R is, I think I went over this with you guys in the scavenger hunt as well. It's anywhere between -1 to +1. So if you were to plug in a very big number or very low number for R, the highest slope that it can go to is positive 5/3 and -5/3. I mean, those two are the only values that it can like go back and forth between from. But it can never go to a slope of 2 or 3. That's just way too high. So the answer is just going to be E from that reason. Consider the 3 points given in a straight line. We can calculate the sum of the squares. Okay, so this one, I actually have to use the calculator. So stat, edit, 2, 3, 4. And then I'm going to do 11, 17, and 29. Stat, calc 4, list 1, list 2, calculate, bam. All right, so that's 9x minus 8 for your least squares regression line. So with that, I'm just going to plug in the values. So if I plug in X and now I have a Y hat now, X plugged in 2, I get a 10. X plugged in 3, I get, what is that? 27 minus 8, which is 19. 36 minus 8, so that should be 28. So the actual Y value though is 11, 17, and 29 respectively. So if I do Y minus Y hat, the residuals for this, Y minus Y hat, that's 1, that's -2, and that's 1. So what is the sum of the squares of the 3 vertical distances? So now I have to square all of these values, 1 squared plus -2 squared plus 1 squared. Like I am literally taking these values and I'm squaring each and every single one of them and I'm summing them up. Oh, that's a 6. That's 1, that's 4, that's 1. So 1 plus 4 plus 1 is 6. Okay. Next, this is the average of all the dots. As you can see, it has a very high leverage. If I were to see that this actually gives you a residual of a straight up flat 0, this will change the residual by, well, the least squares regression by a lot. Does this point have a high leverage or large residual? So now with this point, because it's gonna fall right on where the line is, it's gonna have a very small residual. Okay. So I think 10, 12 was B. Yep. So everything should be correct from that one. Okay. All right. So next question. So we have a line and then there's Mary's point. Obviously we can see that it kind of, without it, I could have something like that looks like this, but because of Mary's data point, it will tilt to look more like that, where it kind of, to make sure that it kind of goes to the Mary side a little bit more. So this is with Mary and this is without Mary. All right, so then I have the equation, find the correlation coefficient. You just have to take that and square root that, and make sure that it the sign matches up with the slope here. So I'm gonna just go to the home screen, square root of 0.746, so it's 0.863. And then so what you're gonna say is, does this ask me to interpret things too? Can find the correlation coefficient. So it's 0.863. I think that's all it says. What is the slope of the regression line? Slope of the regression line is 1.106 for that one. Again, what does it signify? As length increases, okay, so as length, the page increases by 1, your grade increases by 1.106. That's what it means. So as you, what is this for the length of the papers for the research paper? So as length increases by 1 in terms of page, your grade increases by about 1.106 points. How will the correlation coefficient change if the Mary's paper is included? So if Mary's paper was included, your correlation coefficients, I believe, should actually decrease because it creates more residuals overall. So again, let me just verify. So part C, it says, yeah, we'll lower the correlation value. And how do I know that? Well, because, just think about it. If I did not have Mary's dye, I mean, look at the red lines. The red line, and if I were to find out all of these residuals, they're relatively very low. Compared to the residuals from the blue line to all of these dots here, Mary's dot to the blue line, I mean, yes, they're eyeballed and they're very imaginary, but the Mary's dot is like, it's not really following the trend of the line itself originally. It is an outlier, okay? Because if the trend is more pages, more points, I mean, Mary did way more than this particular student did, and they got about the same score. So it doesn't fit in the overall trend of the data. If you plug in a dot that doesn't fall really well with the rest of the group, your correlation coefficient will decrease because your relationship, your association has now been weakened by that one particular point. Okay, so the correlation will decrease definitely because Mary's dot is it has a large residual. It's an outlier certainly because it has a large, well, you don't want to say it's an outlier maybe, but Mary's dot actually makes the overall residuals to increase. I think what they said was including Mary's paper will lower the correlation because her result seems far off from the regression line. Yeah, far off from the regression line means high residuals. How will the slope of the regression line will change if Mary's paper is included? It definitely decreases. Okay, how do you know that? Well, remember your red line is steeper than your blue line. Okay, blue line is more flattened out. So because the blue line is more flattened out, the slope is actually down. Moving on. We've actually done number 2, so I'm going to go over this really briefly. Does the line appear to be appropriate model for this? Yes. You think there might be a curved pattern? I don't see anything. I don't see like, if it's a curved pattern, it should be like literally curved pattern that I could clearly see with the dots. It's a bunch of dots scattered all over the place. I mean, there's not really a pattern here. So yes, because residual plot shows randomness, shows scatter. So residuals show those two qualities. Yes, it's going to be a linear model will be the best fit. Part B, what is the slope of the least squares regression line? It's going to be 0.95893. I don't want to interpret that again. It's basically comparing the year. As year increases by 1, your, what's the computer out, what is it? The winning long jump distances. The distances changes by or increases by 0.95, what is it, meters? With jumps recorded in the inches. Okay, so it's in inches. So as year increases by 1, the long jump increases by about 0.95893. That's how you interpret the slope. What is the correlation? Square root this value. So I will do that one more time for you guys. Square root of 0.921. So that should be 0.9596. Oh, Mr. Kim, what do I have to round it up to? You don't have to round up to anything. Just copy it down to like the nearest 100,000th place. So 10th, 100th, 1,000, 10,000th place should be fine, or whichever that you guys get. Or even if you want to write 0.96, I'm totally cool with that. It just shows you that you understand what the correlation is, as long as you don't write down 0.92. What is the predicted winning distance for the 1980? So you use the equation to predict it. So it's y hat is equal to, well, let's just be more precise here. Long jump distances with a hat is equal to 256.576 plus 0.95893x. So x here being the 1980 competition. So that's 80 years since 1900. So I'm going to plug in 80 into the calculator here. All right, so zooming into this, 256.576 plus 0.95893 times 80, and bam, so that's 333. 333.29 inches will be the predicted amount at 1980. What was the actual winning distance in 1980? It seems like the residual was 2. So the actual is actually added 2 from that, because remember, if the residual is 2, it means your actual is higher by 2. So for part E, that should be 335.29 inches based on that example. All right, so that should sum that up. Draw a histogram of the frequency of the number of accidents. Oh boy. All right, so this one, how are we supposed to do this? This is gonna take a while, but I'm still gonna just do this for you guys, just for the sake of like actually showing you guys what this is talking about. So like you guys are not gonna get a question like this, but let's just do it for the sake of actually practicing what we already know. It says the day number, it's just the number of accidents, so that's a frequency. So this is just a one measurement plot. So I'm just gonna have 1, 2, 3. Okay, so there's, wait, these are all zeros, by the way. Oh, number of accidents. Oh, the number of accidents I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 0 10 times. 0, 0. Okay. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so that's 10 times I have a 0. I have 1, 5, 8 times. So 1, 1, 1, 1, 1, 1, 1, 1. 2, 2, 2, 2, 2, 2. That's 6. 2, 2, 2, 2, 2, 2. All right, and then I have 3 times, 4 twice, and then 5. Stat. So it's second stat plot, turn it on. The histogram should be this one, and then zoom 9, and there we go. So that should be our the histogram, but I'm gonna change my X-Men from 0 to, let's say, 6, and what X scale should be 1 each time. So I hope that should help. Yes, there we go. So your answer key should match something that looks like that. All I did was just type in the data, so this basically means that I have 1 10 times, I mean 0 10 times, 1 8 times, and so on. So that should be your A. Draw a box plot, do the same thing. So plot 1 on, I'm gonna just go straight to this one. Frequency, yeah, that's fine. So zoom 9, and there we go. So it seems like I have zero I don't have any whiskers on the left because I straight up start from 0, and I have way too many 0 dots to, and so your min and your quarter one, they all fall under the same thing. Name a feature apparent in the scatter plot, but it's not apparent. Oh, so this is like going back to like chapter 2 or chapter 1 actually. It's apparent in the scatter plot, but not in the histogram. I like to do D first because histogram always tells you the shape, right? The shape, so the histogram looks something like this, but then the box plot showed you something like that. So name a feature and apparent the scatter plot. Oh, the scatter plot, but not in the histogram or dot plot here. Okay. All right, so the scatter plot here, yeah, so let me answer part C. The scatter plot shows that there's gonna be generally as the day number, we're comparing the day number versus the number of accidents. So this is 2 variable statistics. The number of accidents tends to have a non-linear relationship, I believe. I think that's what they said. There is a roughly linear trend with daily accidents increasing during the months. Oh, wow. Okay. So there is a linear trend as X increases during the month. There's a roughly linear trend with daily accidents and the number of months here. Okay. There's a linear relationship. Okay. I don't buy that. Okay, so name a feature apparent. So there's gonna be either like a linear relationship or a non-linear relationship. I quite honestly, if we're talking about the number of accidents at 30 being at 5, but at 25 around being at 4, but this is I just believe that the daily number of accidents per number of days, it should be more of an exponential graph here. So I would say, but as again, the scatter plot shows always some sort of a level of degree of association between 2 variables. Well, obviously histogram and box plot can't tell you that. They only measure like 1 variable statistics. They only measure one thing. Name a feature clearly shown by a histogram and box plot, but not as obvious in the scatter plot. The shape is definitely shown. The shape of the overall distribution of the curve. I believe that's what they said. The daily number of accidents is skewed to the right. I mean, that is pretty much what this is talking about. And because the box plots, you can never tell the shape, but you can give an extension for this because this just simply means that if you have no whiskers on the left, all the data is so congested on the left-hand side that it just begs to say, okay, I'm going to have this as a skew to the right distribution because the tail is on the right-hand side, but I have no tail on the left. All the data is congested on the left. So that is really the main difference between the two. I really don't agree with the linear idea for part C there, but you can just say from the scatter plot, you can see that the association or some degree of level of relationship between 2 variables, but you can't tell that from histogram or box plots. And part D, shape, skewed to the right. You can't tell that from looking at this. All right, last question for quiz 9. In a study, we have, okay, so we have these hours of sleep versus exam scores. Describe the association between the exam scores. So let's draw a line like this, it seems like. First of all, this is very weak. I hope you guys can also see that as well. There's an example of moderate on the previous quiz, and you guys know what like a strong looks like. This is certainly weak relationship, but it's definitely positive. We can see that we can see that trend happening from left to right. It's weak and it's linear. So remember form, strength, and the direction. Describe the association between exam scores and the hours of sleep for the 8 students who received at least 6 hours of sleep. So we're talking about these blue dots right there, 5, 6, 7, 8. All right, so it's all over the place. If we're just considering this part of the data, okay, I mean, I'm gonna erase these 2 lines and just bring this down for you guys to see. I mean, if I were to ask you guys to draw a best line of fit, some of you guys might kind of argue that it might look something like this. Okay, and I do agree with you on that one. But then the problem with that is that there's just all of these dots here in the beginning. They all fall under somewhere between 6 and 7, but they have so much different varieties of exam scores that they give you. Remember, the best line of fit, always you want to draw it in such a way that it kind of goes over half of the dots going above and half of the dots going below. So you might draw something like that there, right? Or I can just use one of those. You can use the website to kind of plot the points approximately where they are and then see for yourself as to what the line is going to give you. But the association between the exam scores of hours of sleep for 8 students who got at least 6 hours of sleep, it seems like, you know, these dots are very vertically just all over the place, that the X value doesn't really impact the outcome of the response variable. So there's little to no association. We don't want to say that this is a positive association because, I mean, we're going from 6 to 7. It doesn't really measure much of the X variable for us to kind of say like this, unfortunately. So this one, we want to say that there is to be little, if not there's any association between those 8 dots, blah, blah, blah. Fill in the context, you get the idea. Part C, explain how the appropriateness of using linear regression is critically influenced by one student's data. All right, so this one, again, it's very ambiguous as to how the answer key said it. But we have, I think you guys can all agree with me that it's got to be one of these 3 points. I mean, if I were to draw a best line of fit somehow, okay, let's say that I do a better job with that. So something that looks like this, okay? So you draw the best line of fit and you can kind of see that, okay, this part right here, we answered it from part A and B that it's just all over the place and there's really not that much relationship going on amongst those guys. So how does 1 point critically influence the overall aspect of, you know, all those dots? These 2 dots that actually falls after 6 hours of sleep, they do not really have a much impact because when they're put together, they actually balance each other out in terms of like drawing the best squares regression line. If this dot wasn't here, then this dot will heavily influence the line to be tilted up that way. But because this and this is kind of there, your line will still kind of go through the middle, if that makes sense. The one that actually poses the most influence on this particular line will be this point. So this is clearly much of an outlier. I mean, obviously it has a high residual. These 2 does. They also have a high residuals too. But this is 2 hours of sleep, getting an exam score of some like 75. You know, comparing that to all the other data and statistics out there, like you don't expect that to happen with this line. So this dot will clearly tilt this equation. Without it, like if I were to exclude this dot right there, I would much rather have the line to draw like this. Much more appropriate to have it somewhere, it's going to be tilted upwards. That dot heavily influences so that it gets tilted in such a way that your y-intercept is now starting at a very higher range, because this actually brings the overall average up for those people who did not get any hours of sleep. And also it's going to lower the slope. You know, it's going to, because it tilts it this way, makes it less steeper. So explain how the appropriateness of using linear regression is clearly critically influenced by one student's data. The linear regression is critically influenced. They say that because of this point, the non-linear form will be a better fit or something like that here. The student who scores 75 before the exam shows a strong influence. The particular a scatter plot point taken together with all the other points suggest a non-linear format. Again, if I have this right here, I think there should be clearly a trend as to a non-linear relationship happening in those particular points. But because of this dot, it's actually going to make it so that it's going to be much more of a using a linear regression line. This point actually makes it so that it's going to make it more into a line rather than an exponential model. Okay. All right. So that's basically what this is talking about. So I hope, you know, again, the wording it's so sometimes very bad, but this is not an official AP College Board test. On those, it should be a lot clearer in terms of open-ended questions. Again, you still want to do your best though. Just write down your thoughts on this, but explaining this one, appropriateness of using linear regression. I mean, you can probably see that too, that there is a clear non-linear trend happening in the midst of all those things. But because of this dot, now that dot just changes the game overall. It's clearly an outlier that actually makes a linear form to be a better fit than a non-linear form. All right, so that is it for quiz 9. I hope this helped, and I'll see you guys in the next video. Thank you guys so much. Have a good day.